Okay, we are welcome Dr. Fumika Suzuki for the first presentation of today. Yeah, welcome. Have a screen.
Okay, so thank you for coming to my talk. So I'd like to talk about Anderson localization of composite particles, and those are our collaborators. So our motivation was that although previous studies of Anderson localization have been done with a structureless particle, recent experiments with outer-cold molecules suggest the possibility of observing Anderson localization of quantum particles with internal structure. So for example, it is now possible to trap outer-cold molecules in optical lattices. And this enables us to study the effects of molecular low vibration structure on Anderson localization of outer-cold molecules. And we also have that quantum dynamics of composite particles can be largely affected by internal degrees of freedom. For example, it was observed that long-lived resonances or bound states in continuum can be formed around repulsive delta potential by those composite particles. And this kind of phenomena cannot be seen with a structureless particle. And on the other hand, those composite particles also can have decoherence due to internal degrees of freedom. So for example, even if we have the spatial superposition state of a composite particle, those internal states can be excited differently depending on whether the wave packet is located left-hand side or right-hand side, and when the internal state traces out due to, for example, coupling with radiation field, those superposition states can decohere. And we show the same thing happens for BX atom. So if I make interference pattern made by composite cohesive particle like BX atom and interference pattern made by a single particle, we can observe loss of quantum interference visibility due to the internal degrees of freedom. And one of the most famous examples of decoherence due to internal states was done with C70 molecules by Zallinger and An's group, and they observed that the superposition state of C70 molecule can decohere by thermal radiation from internal degrees of the molecule itself. So it is a little bit strange that we have the internal degrees of freedom, and that can be the source of decoherence. However, for large molecule like C70 molecule, we have the numerous degrees of internal degrees of freedom, which can actually act like thermal reservoir or environmental thermal bath and cause decoherence. And now, if we look back to another localization, what is known is that for a structureless particle in 1D or 2D, all states are localized, and in 3D, we have mobility edge, which is the energy that separates localized and delocalized states. And for a composite particle, there exist internal degrees of freedom, which can act as additional dimensions, even if dimension for its center mass is 1D or 2D. So first question we want to address is how does additional dimension from internal degrees of freedom affect Anderson localization of composite particle in center mass coordinate or translation coordinate? And another thing is that localization can be understood as interference phenomena, for example, using path integral formalism. So for path integral formalism, if I want to calculate the probability for a particle going from point A to point B, we sum over amplitude associated with each path, and we make a square. And then in the probability, generally we have a quantum coherence term. However, in the disordered lattice, this potential is so random that the amplitudes associated with different paths just interfere with each other destructively, and the coherence term cancels out. However, we have the exception that when the particle comes back to its initial point by making a loop, we have a time reversed pair of paths going clockwise or anti-clockwise. And those paths have identical amplitudes, and they interfere with each other constructively, even if in the random potential. And the probability that a particle comes back to initial point is higher due to the non-vanishing coherence term for the loop. And so second question we want to address is that we have a decoherence due to internal states. And what is the effect of this decoherence as localization as interference phenomena? So this is the last slide for our motivation. So our question is, what is the effect of the coupling between translation and the internal states of composite quantum particles on the localization? And especially we focus on whether internal degrees of freedom can be considered as additional dimension or source of decoherence. And here I will talk about two models. So firstly, I will talk about two particle system bound by a harmonic force in 1D disordered lattice. And secondly, I will talk about rigid rotor of two particles in 2D disordered lattice. And our study is different from many body localization because although two particles are interacting with each other, they are already bounded in the relative distance and they are moving together. And therefore, we are only interested in its localization of the composite particle in the translation coordinate. And secondly, our question is also a little bit different from the single particle Anderson model coupled with environmental bars, because internal degrees of freedom can be the source of the coherence, but it can have generally have a smaller dimension compared to the ambient environment bars. And secondly, the coupling between translation and internal degrees of freedom can be determined by quantum dynamics of the composite particle as a whole in the disordered lattice. Okay, so here is our setup. So in order to study Anderson localization for a composite particle, we consider a pure state of a composite system, and the dimension of the subsystem S is ds, and the dimension of the subsystem E is d. And for a composite quantum particle, S represents translation position by R, and E represents internal degrees of freedom by N. And because we are interested in the localization in the translation coordinate, we trace out internal degrees of freedom and obtain the reduced density matrix of S. And then localization of the subsystem S in coordinate R can be quantified by inverse participation ratio, Ipr, which is a sum of the square of the diagonal element of the reduced density matrix. And this Ipr, which I represent by psi, is roughly equals to 1 over number of sites occupied by the wave function. So if we have extended states, this Ipr goes to 1 over ds, and we have a wave function spread over all space in the translation coordinate. And if I have a localized state, Ipr is constant, which is much larger than 1 over ds. And only single site is occupied, Ipr is 1, and we have the wave function is strongly localized in the translation coordinate. And on the other hand, the mixing of S and E can be quantified by purity, which is like von Neumann entanglement entropy measures the entanglement between S and E. And we can easily show that this purity should be always larger than Ipr. Therefore, the purity puts an upper limit on Ipr. This indicates that if we have a strong entanglement between S and E, purity decreases, and therefore the upper limit on Ipr also decreases, and the localization can be weakened. And it is known that this purity takes a value from 1 over d to 1, where d is the minima of the dimension of the subsystem S and subsystem E. So when the dimension of the subsystem E, which is traced out, is larger than the dimension of the subsystem S, which I look at the localization, then Ipr goes to 1 over ds as S and E get strongly entangled, because purity goes to 1 over ds when S and E get strongly entangled. And because this is upper limit of Ipr, Ipr also goes to 1 over ds and states get extended. And this situation is relevant with a quantum particle coupled to the environmental bars. So here we have the coherence in this extended states when the system and the bars are maximally entangled. And this is consistent with the interpretation of localization as interference phenomena. So the coherence due to the coupling with the environment destroys the localization as interference phenomena. And more generally, even when the ds is larger than de, for example, the case for our study, internal degrees of freedom, we still have the purity gives the upper limit on IPR, so it may happen that localization can be weakened. And I'd like to mention that this delta, which is a ratio between IPR and purity, can be a useful tool to characterize quantum states. So for example, when delta is roughly equal to 1/ds, state delocalized already in the absence of environment. On the other hand, when delta is from 1/ds to d/ds, we have a localized state with purity is equal to 1, or delocalized state with purity less than 1. So here we have the mixture of localized and delocalized states, and delocalization can happen induced by decoherence. And finally, when the delta is much larger than d/ds, we have localization even with couplings to environment. Okay, so do you have any questions so far? Okay, I just proceed. And so in our study, we are looking for delocalized state with purity less than 1, and whether the delocalization happens due to decoherence by internal degrees of freedom. And so firstly, I will talk about Anderson model for 1D harmonic oscillator. And here is our Hamiltonian. So we have a creation operator for harmonic oscillator with translation position R and internal vibration state N. And J is the hopping strength in the translation coordinate. And we have the energy for the internal vibration states. And omega is the frequency of the internal vibration state. And we have the effective potential made from the random potential from the disordered lattice and wave function from the internal vibration states. And we take lambda random values from a uniform distribution over minus lambda to lambda. So that lambda gives a disorder strength. And we can derive this Hamiltonian by looking at Hamiltonian for two particles interacting with each other in a disordered lattice. And so here we have the interaction between two particles is a harmonic potential for harmonic oscillator. And then we derive this Hamiltonian in terms of translation coordinate large r and relative distance small r. And we also introduce the operators associated with them. So large r hat makes the translation position hop by 1, and small r hat makes a relative distance hop by 1. And then we can rewrite this Hamiltonian in this form. And we finally project the Hamiltonian onto the set of states of the harmonic oscillator. And we obtain the Hamiltonian, which I showed in the previous slide. So this one. And we diagonalize this Hamiltonian and look at the behavior of its eigenstates. So here I plotted the distribution of eigenstates of Hamiltonian. So we have IPR and purity, and left-hand side we have weak disorder, and right-hand side we have strong disorder. And so what we observed is that as disorder strength gets larger, the distribution comes close to upper limit where purity is equal to IPR. Therefore, the upper limit given by purity, so this solid red line represents a line where purity is equal to IPR. And therefore, the upper bound given by purity becomes important when the randomness is large by preventing IPR from becoming larger than purity no matter how large the disorder strength gets. So we have the limitation of the localization strength even when the randomness is very large. And we also observed that as purity decreases, IPR also decreases. And another thing is that we also can compare the IPR from the structuralist particle. So those black solid line gives minima and maxima IPR for the structuralist particle. And we observe that for the composite particle with purity less than 1, we see that maxima IPR for the composite particle is much suppressed compared to that for the structureless particle. And finally, we can also look at the average IPR for each energy for the composite particle, which is a thick red line. and the structureless particle, which is blue solid line. And we see that generally IPR for a composite particle is less than that for a structureless particle. So we have the coupling between translation and the internal degrees of freedom can suppress.
Excuse me,
do you have any questions?
How do you define a structureless particle in this context? So what are the properties of the structureless particle?
Structureless particle is just a point particle, which is studied in the conventional Anderson model. So just it's
a point particle. Yes, that I do understand. But what are the hopping matrix elements, or what is the effective mass of this structureless particle that you can compare with the harmonic oscillator?
Okay, so harmonic oscillator have internal degrees of freedom and translation motion. So yes. I choose translation motion for the harmonic oscillator should be same for the structure.
So is it to say that that you just take the limit of infinite stiffness for the harmonic oscillator? Is it the same?
We have the effective potential. So if we have two particles together, both particles interact with this delta potential. So the potential can be higher for a harmonic oscillator, but except that it's same.
Right. Okay. Thank you.
And I also studied the time evolution of wave packet initially localized at the origin of the lattice. And here, what I want you to show is that the different omega frequency of the internal vibration states control the coupling between internal and translational motion. So here we have the wave packet initially localized at the origin of the lattice, and initially the internal vibration states in the ground state. And when omega is small, what happens is that as the time evolves, purity and inverse participation ratio decrease with time. On the other hand, when omega is large, well, we see that the IPR and the purity comes back to close to 1 periodically. And this happens because when omega is small, as the time evolves, so this is a population with the excitation with the internal degrees of freedom, and the black dotted line for this left panel is initially 1 in the ground state, and as the time evolves, the population of the ground state decreases with time when omega is small. On the other hand, excited states get populated. However, when omega is large, excited states do not get populated because the energy transfer between translation and internal degrees of freedom is not enough to excite internal degrees of freedom. So for omega is large, we always have ground state populated around 1, and the translation and the internal degrees of freedom get decoupled. So energy transfer between translation and the internal degrees of freedom is necessary to have a coupling between 2 degrees of freedom. And in such a case, we have a weakened localization. And we can also look at from this Hamiltonian. So this Hamiltonian effectively describes a 1 plus epsilon dimensional system where epsilon is accounting for internal states. So it is kind of quantum dynamics on a Cartesian product of a lattice graph for translation motion and a complete graph for internal degrees of freedom. And for large omega, we have that transitions between different internal states do not occur. So 1 plus epsilon dimensional problem reduced to a 1D problem for each internal state. And the purity close to 1 means that those 2 degrees of freedom are almost separable in this Hamiltonian. And we can also look at the scaling of IPR as a function of the number of lattice sites. So here, red line represents composite particle on the harmonic oscillator with small purity, and green line shows a harmonic oscillator with large purity, and the dotted line is for structureless particle, and I increase the number of lattice sites from 50 to 450. And for high omega, what I observe is that this green line, so this psi is IPR for the translation coordinate. So this psi just to represent a localization in the translation coordinate, and this psi tilde is IPR for the whole 2 degrees of freedom without tracing out internal degrees of freedom. So this psi tilde measures the localization in both translation and internal degrees of freedom. And then what we observe is that for high omega, so this green line, psi tilde goes to psi. So this behaves similarly when the omega is large. And therefore, we also observe that from the scaling of Ipr, that 1 plus epsilon dimensional problem is reduced to 1D problem from the scaling. On the other hand, when omega is small, we have the purity is small, those I are psi and psi tilde behaves differently. So for low omega, we also observe that the IPR for the oscillator is much less than IPR for the structureless particle. So what happens is that for low omega, this psi and psi tilde behaves differently. And so we have the contribution from the internal degrees of freedom. And in such a case, we have that IPR for the oscillator is much suppressed compared to that for a structureless particle. However, even this red line doesn't go like 1 over ds. So unfortunately, we didn't observe extended states for 1D harmonic oscillator. And however, we saw that localization can be weakened if we have a strong coupling between internal and translation degrees of freedom. So this is the result for 1D harmonic oscillator. And now I would like to move to adapt a model for a rigid rotor into 2D disordered lattice. So here we have the Hamiltonian for the model. And now we have the creation operator of the rigid rotor with the translation position R. And now this is in the 2 dimension, and we have the internal state N. And En is the energy from the internal rotation state, and small r is a fixed distance between 2 particles of the rod. And we have the effective potential made from the random potential and rotational wave function from the internal rotation state. And similarly to the 1D harmonic oscillator case, we can derive this Hamiltonian by looking at two particles interacting with each other in 2D disordered lattice. However, now particle-particle interaction is for a rigid rotor. So this particle-particle interaction is 0 if the relative distance between 2 particles is r, which is a length of the rod, and this goes to infinity otherwise. And again, we introduce a translation coordinate and a relative coordinate in the 2D lattice, and we rewrite this Hamiltonian in this form. And finally, we project the Hamiltonian onto the set of states of the rigid rotors, and we obtain this Hamiltonian. And now I look at the scaling of Ipr. And then here, what I did is that I increased the number of lattice size from 20 times 20 to 60 squared. And then for the rigid rotor, what we observe is that when purity is small, so for red line, it is much suppressed compared to for the structureless particle, which is represented by black dotted line. But more importantly, this red line goes like, IPR goes like 1 over ds for small purity. And therefore, coupling to a few internal states. So in this case, I had 3 internal rotation states. And this coupling largely accelerates the scaling of IPR. And we have the possible formulation of extended states, even if the rotor itself is on 2D disordered lattice. So even if the 2 rotor is moving around in the 2D disordered lattice, it has a hidden dimension from the internal degrees of freedom, and it can cause that it may create an extended state, and we found a signature that it may happen that extended states can be formed by looking at scaling of IPR. And then one may ask whether this 2D rigid rotor model has mobility edge or not. So here we plotted IPR, which I represented by color. So whitish color, we have a small IPR, and darkish color, we have a strong, large IPR. And here we plotted IPR as a function of disorder strength and energy expectation for the translation motion. And then we see that as the disorder decreases, disorder strength decreases and energy increases, we have a whitish color, which means that we have extended states around here. And however, if I look at the behavior of ion states in more detail, what we observe is that not only energy, but the purity plays an important role to create extended states. So for example, I choose lambda equals J, and then as the purity decreases and energy increases, we have extended state, which is whitish color here. However, even here we have the mixture of localized and extended states. And therefore, it seems that 2D Rotor Anderson model is more complicated than 3D structuralist particle Anderson model, because for 3D structuralist particle Anderson model, its energy mainly determines the localization properties, and therefore we have the mobility edge, which is the energy that separates localized and extended states. However, for a rigid rotor, it seems that we also need to look at the purity, which measures the coupling between two internal and translation degrees of freedom. So we do not have a clean separation between extended and localized states in this case. So to summarize, the internal states of a composite particle can induce decoherence and can weaken localization's interference phenomena in its translation position. And the internal states also can act as an additional dimension and can induce extended states for the composite particle in 2D disordered lattice. And as an example, we look at the 2D rigid rotor. And for 1D harmonic oscillator, we didn't observe the signature of the extended states, but for 2D rigid rotor, it may be possible to have extended states, and we found the signature by looking at the scaling of Ipr. And those effects are remarkable when purity is small and the translation and the internal degrees of freedom are coupled strongly. And this strong coupling happens when the translational energy is comparable to the energy of the internal states, and energy transfer between the 2 degrees of freedom can excite internal states. And Hamiltonian becomes inseparable in translation and internal degrees of freedom. And so we looked at the Anderson model for a composite particle, and it seems that it can exhibit rich complex phenomena compared to that for a structuralist particle, which can be studied maybe further in future. Okay, so thank you for your patience, and yeah, thank you.
Questions?
Right, I have a question. It's Vadim Chianov from the auditorium, from the room. This business of a particle with a structure, or rather two interacting particles trying to localize in a one-dimensional potential is quite old. And the first work on this subject appeared in 1994. It was by Szczepilański, and he concluded that for two interacting particles on a one-dimensional lattice, there exist states which have localization length much greater than the localization length of an individual particle. So that was a conclusion. And he also mapped that problem onto a certain band matrix, random band matrix problem. Then these results were confirmed by Ipr the next year, and then a couple of years later, Romer and co-authors argued that the numerical results by Szczepilański were actually an artifact of finite system size. And the results may be held in a certain limit, which is not available numerically, which is a limit of extremely strong interaction. And then the same arguments were developed further by Flach and Quartus in 2011. So the whole business has a very long history, and one of the and it is quite controversial. And one of the important conclusions from that particular example is that you can't rely, if you try to make conclusions about localization, delocalization transitions, ergodic, non-ergodic transitions, and mobility versus localization in terms of transport transition, in either of those cases, you have to be extremely careful about drawing conclusions from numerical simulations. Now, your model is slightly different. It's quite different, actually, from Shepelyansky model. Can you comment if your model, if you know about this business, if you can compare with that business, is your model more advantageous in terms of this numerical analysis? Is it better suited to draw conclusions about the finite size lattices?
So in the order model, two particles are in the scattering state or in the bound state? So
well,
do they move together or?
Right, the difference, okay, so Shepelyansky considered a system of particles with a, he made an argument about this system of particles with an arbitrary interaction, but he in particular, in terms of numerical simulation, he considered a system of particles which repelled each other. And his conclusion was that if the distance between the particles, so if we consider a quantum state where the distance, the average distance between the particles is on the order of localization length or less, then such a state can propagate a much greater distance than each individual particle if they had not been interacting. That was the conclusion of the paper in 1994. Now, your model is slightly different because in your model, you can't actually separate the particles a lot without paying a lot of energy for that. Although this separation is technically possible, it is not impossible, but you pay a lot of energy for that. That's not what was the case in Shepelyansky. In his case, he considered a local or short distance interaction between the particles, but the conclusion was sort of similar to yours, except later on, people started arguing that this conclusion was based on a numerical artifact because Shepelyansky worked with a small system, and I'm worried slightly about your situation. Could it be that your results, in analogy with that previous body of work, your results are not as reliable if you go thermodynamic transition or large system size transition?
So what was the last question? Sorry.
Again, there has been a long history of of people studying this problem, and one of the main conclusions is that numerics is not reliable. If you analyze the localization properties of such an interacting system, and although the model was slightly different than yours, because it considered short range interaction between the pair of particles. So that was a slightly different model. But the important conclusion from that analysis was that the numerical data obtained in a finite size systems is not entirely reliable and actually can lead you to completely misleading conclusions. So my question essentially, are you familiar with that body of work? And if you are, can you highlight the important differences between that body of research and your model, which is indeed slightly different?
Yeah, I think the big difference is that in our case, two particles are moving together. However, for the older studies, I think we have two particles which is not bounded to each other, right?
Yes, that's essentially correct.
And And then if I have two particles together, we can write the Hamiltonian in the internal states and translation motion. And so what we used more smaller dimension compared to the two lattice dimension for the two particles.
Yes.
Yes. And
okay, so
yeah.
I see. Okay, so your point is that because you can truncate your Hilbert space a lot in your case, your numerical results are actually reliable as compared with the Shepelansky work, for example.
Yeah, that is what I'm hoping. It's, of course, that if I can solve it in mathematical physics formalism, it is nicer, but I think it is a first attempt to study Anderson localization of kind of composite particle, which is bounded together in numerically.
I see. Okay, yeah, thank you very much.
Thank you.
Sure.
No, you can even do this.
Okay. Hi. I'm also from the audience, Tobias. You motivated that you could well carry out this experimentally, or one could carry out this experimentally with molecules which you trap in a lattice. So now I'm wondering what your observables would be to. So of course you can see the size of the cloud, but what else can you get out of these experiments, or what would you imagine? And what happens if you add interactions to the system? So did you think of these directions?
Interaction.
So you're looking at only two particles which are bound.
Yeah.
But you're motivated with the idea that one could use molecules, and then you would not use a single molecule, but I guess you would use a cloud of molecules. So now I'm wondering what this means if you would try it experimentally.
Okay. So if you have molecules and if you could study Anderson localization of the molecules, it has a larger number of internal degrees of freedom. So which I think it's better if you want to have a delocalization of the states rather than our models. And another thing is that when I was talking this in the conference, some people were interested in if we can do the same thing with two molecules interacting with each other, and if they can study many body localization thing.
Based on two particles, you say?
No. So if you have a molecule, even single molecule, you have a numerous number of degrees of freedom, which can affect Anderson localization. So if you want to have a delocalized state, I think it's better. And secondary, other people may be interested in you put more molecules and interacting with each other and study many body localization with each molecule have internal degrees of freedom. That was I was told by audience in other conference.
Exactly. No, that was where I want to point to. So what from your work would apply to this, or could you extend it to this regime?
Yes, I want to try. So here, most relevant setup is BX in the to this disordered lattice or disordered lattice.
I see.
Yeah.
Okay, thanks.
Yeah.
More questions? Hey, online people, we're waiting questions from you as well. Not so much? Так, okay. So then I'm stopping recording. Так. Thank you very much for the presentation.